Hello everyone, welcome to my YouTube channel. Today we are going to study degrees of freedom. Degrees of freedom for a structure is total number of independent joint displacements and rotations. First we'll look at degrees of freedom for space structures. Or we can call them three-dimensional structures. For example, this is a 3D structure, and structure is called space structure if its members and loads lie in three-dimensional space. And we very well know that to describe systems or structures in three-dimensional space, we need a coordinate system with three mutually perpendicular axes. Now, because this structure lies in space, any point in this structure, say for example point A, this will have displacement and rotation vector which will lie in space. And we know that any vector that lies in space has three independent components. So for joint A, we will have three components for displacement vector and three components for rotation vector. So in total, joint A will have 6 independent displacement and rotation components. So for a joint that is A in this example, we have 6 degrees of freedom. Out of these 6 degrees of freedom, 3 are displacement degrees of freedom, which we can denote by ux, uy and uz, and 3 are rotations, which we can denote by theta x, theta y and theta z. So if we want to find degrees of freedom for entire structure, we add the degrees of freedom for each joint in the structure. Next, let's move to a planar structure. Or 2D structure. A 2D structure or a planar structure is one in which all the members and forces lie in a plane. So for example, this is a planar structure and forces lie in plane. And as we know, we need coordinate system with two mutually perpendicular axes to describe planar structures. Now in this structure, if we look at joint A, and before we look at the displacement and rotation vectors, let's first understand one thing, and that is the relationship between the rotation and rotation vector. Here in this example, we have a clock, and the second hand of this clock is rotating in clockwise direction, and this hand, as you can see, always lies in xy plane. It does not move out of the plane. And if we use curved arrow notation, then rotation of this hand is denoted by an arrow which is curved in clockwise sense. But the rotation vector of this movement or rotation does not lie in the plane. The rotation vector lies perpendicular to this plane, and the direction of rotation vector is described using right hand thumb rule, which says that if I turn the fingers of my right hand in the direction of rotation of the object, then my thumb will point in the direction of rotation vector. So in this case, if I turn my fingers of right hand in the direction of rotation, then my thumb will point in direction of z axis, and that will point inward. So that is negative z axis. So in this case, my rotation vector will be pointing inward perpendicular to the plane of the screen. And if you want to write that in vector notation, then I can write that as theta vector is minus theta k cap. This minus denotes the direction is in the negative z axis, and k cap is unit vector for z axis. So for rotation in a plane, the rotation vector lies perpendicular to the plane. So here our joint A will rotate in the plane, say for example like this, then the rotation vector for this displacement will be perpendicular to the plane and will be denoted by theta z. But the displacement vector lying in the plane will have two components, namely in x and y direction. So for planar structure, a joint will have 3 degrees of freedom. Out of these 3 degrees of freedom, 2 will be displacement degrees of freedom, which we can call ux and uy, and 1 will be rotation degree of freedom, and that we can denote by theta z. So if we want to find total degrees of freedom for a structure, then we add the degrees of freedom for all the joints in the structure. Thanks for watching this video. If you find this useful, please like this video and subscribe to my YouTube channel. Thanks for watching.